Good day, scholars. This is Mrs. Jones with your ionic bond lesson. So let's get started. We have ionic bond. Ionic bond compounds are composed of positives and negative ions that are combined so that the number of positive and negative charges are equal. So we have a neutral net charge. Ionic bond occurs between metals and nonmetal elements and has an electronegativity difference greater than 1.7. We'll get into that more in class. Also, the nonmetals has a higher electronegativity than the metals. The valence electron of the metals are transferred to the nonmetals. The number of electrons gained or lost will be equal to the number of electrons needed to form octet of 8 electrons. Remember, the octet rule is coming back. Also, here's an illustration of formation of ions, particularly cations. Here we have lithium atom, the neutral lithium atom, with its 3 protons and 1, 2, 3 um, electrons. It has one valence electron. Here it is. That one valence electron gets lost, and then when it gets lost, it forms something called a cation. Make sure you write down this illustration, this Bohr's model diagram. When it loses its electron, it now has 1, 2 electrons and 3 positive protons, making it a lithium ion with 1 positive charge. This is a stable configuration. We want all of our atoms to have the octet. Now, the formation of anions, which are negative. So we're going to start off with the neutral atom of fluorine with its 9 protons and 1, 2, 3, 4, 5, 6, 7, 8, 9 total nine total electrons, but let's focus on the valence electron. It has 1, 2, 3, 4, 5, 6, 7. So fluorine is just 1 electron short of having an octet. So what fluorine wants to do is gain a valence electron, and when it gains an electron, it becomes an anion, which is a negative charge. So we will put that extra electron here on the last energy level, making this fluorine the ion with 1 negative charge. Again, a stable configuration of electrons. Now, what happens is in ionic bonding, this lithium anion with its 1 positive, when it loses its valence electron, it moves in to fluorine, giving fluorine 1 negative charge. And this is known as ionic bonding. There are a few things we need to recall, such as why our atoms form compounds. Well, they form compounds to gain stability and to reduce potential energy. That's most effective. And atoms always want to be stable. And the way to be stable is to have the noble gas configuration of 8 valence electron, which is known as the octet rule. Be sure to add these things into your notes. So here's a short video of how that works. I hope and please. Oh, the video doesn't play here. Okay. Well, moving on. We have ionic bonding. Um, so, most ionic compounds exist as crystalline solids. All right. Crystalline solids are three-dimensional structures or a network of positive and negative ions mutually attracted to one another. So we know opposites attract. And when they attract one another, they form something called a crystal lattice, like this illustration here. A repeating pattern, tightly packed ions that forms a crystal lattice. So from there, we're going to focus on the energy that it takes. Okay? A compound's lattice energy indicates its strength. Oops, spelling strength wrong. Of the ionic bond. And the amount of energy given off by the formation of 1 mole of ionic crystalline solid is known as a lattice energy. So that's the amount of energy that it takes to make this crystalline structure here. That's called lattice energy. Be sure to add this in your notes. All right, so ionic bonding. The chemical formula for an ionic compound is called a formula unit. So, a formula unit is the chemical formula for an ionic compound. This is a ratio of ions represented in the crystalline structure. The simplest whole number ratio of ions, a formula unit of a compound. So here's, for instance, there's one sodium sodium, and then there's one chloride atom. So the formula unit for this would be NaCl. All right, so there are certain properties that ionic compounds have. They have high melting points, and they also have high boiling points. Therefore, most ionic compounds are solid and room temperature. And because they're solid at room temperature, it makes them hard but brittle and rigid. So if you apply force, you could shift the lining of the ions and like kind of chop off or make a nice clean cut, lining up the charges. Now, there are properties we want to focus on. So, conductors of electricity in molten state, which means melted ionic compounds. Molten means melted. Or dissolved in a solution. Ionic in the solid state, ionic compounds would not conduct electricity. When it's melted or dissolved, ions are free and can conduct electricity. Be sure to get this in your notes. Next up, we're going to talk about representation of ionic compounds. It's known as electron dot diagram or Lewis diagram. So electron dot shows the number of valence electron an atom has. So pause the video and make sure you copy down this diagram. If an element has one valence electron, then you will put the element symbol and one dot, like lithium here. If the element has three valence electrons, you would put the element symbol and with three dots around it, like boron here, and so forth. So please copy down this diagram. So write, give it a try. Give it a try of writing the example of the practice problem of calcium, sulfur, and aluminum. Sorry, write the dot diagram for sodium, magnesium, aluminum, silicon, chlorine, and argon and helium that's on your note sheet. And here's the answer for those metals and nonmetal element dot configuration. Next up is understanding how the dot diagram really works. So let's start over here. Nonmetals gain electron forming a negative anion, while metals lose electrons forming a positive cation. All right. So to represent an anion, we put 8 dots around the symbol of the element to represent a gaining electrons to make a complete octet. Brackets are around the symbol of dots, and we write the charge outside of the brackets in the top right corner, as illustrated here for chlorine, or chloride, I should say. Next, for the representation of cations, we put 0 dots around the symbol to represent the losing of electrons on the valence level. Brackets around the symbol, and then we write the charge outside the bracket at the top right corner, such as this here. So please write those things down for examples. Now, why don't you practice calcium, sulfur, aluminum, and bromine samples? Take a minute and pause. Here's some examples that you could add to your notes. There's beryllium, boron with its +3, beryllium with its +2, samples of cations, and then fluoride with its -1, oxide with its -2, and nitride with its -3. And here are the dot representation of the practice problems you were to do. So, next up, ionic compounds formation equation. Lewis structures or dot notation, whatever you like to call it, are used to show the valence electron. So here's a neutral lithium and a neutral chlorine. And once lithium loses its valence electron, it moves into chlorine. It becomes lithium with one positive charge and chloride with one negative charge. So remember, when you're writing these, cations are always written first. And remember that the net overall charge must equal 0. And here's some examples of that you could add to your notes. Now we have some practice problems for you to try. Calcium would be Ca with 2 positive charge, with sulfur gaining 2 extra electrons will have 2 negative charge. Okay, magnesium has 2 valence electron, where bromine has 7 valence electron. So when magnesium loses its 2 valence electron, it has a 2 positive charge. But we need 2 set of bromines, because bromine really needs 1, but we need 2 of them to compensate for the 2 valence electron that's going to be lost here. And that will give us the 1 negative charge times 2. Gives you a total of 2 negatives. Over here we have aluminum with its 3 valence electron. Sulfur has 6 valence electron. So aluminum will have to lose its 3 valence electron. Sulfur needs to gain 2 valence electron. So we're going to have to do this thing called crisscross. This 3 is going to be placed here. We need 3 sets of sulfur to go with the 2 sets of aluminum. We'll get into that more later. Same for potassium. Potassium loses 1 valence electron, while oxygen gains 2 valence electron. Therefore, we need 2 potassiums to satisfy oxygen need of 2 valence electron. Okay, next up, we're going to discuss something called polyatomics. Polyatomics, a group of covalently bonded atoms that bond in such a way that the group of them have a net charge, either positive or negative. Charges on a polyatomic are like other ions, a result of either a gain or loss of electrons. All right. So please be sure to write down this sample of NH4 in your note packet. So to move right along, here we have the first step. The first step is to count the number of valence electrons to be accounted in the structure. And nitrogen has 5. Hydrogen has 1 valence electron, but because there's 4 of them, we multiply 1 with 4. It gives us a total of 9, but we only can have up to 8, so we have to minus 1. Therefore, that's how we get this positive charge on this polyatomic. Now, when you write this Lewis structure for a polyatomic or any covalent compound, the center atom will be the one that has the least electronegativity, or it may be carbon if carbon is present in the formula. Hint, hydrogen will never be the central atom because it only forms 1 bond. And carbon is more, if more than 1 carbon is present, they will both be attached to each other in the center. So here is a detailed diagram of it. Step 3, you add all your dots so that you can have the octet. Then you will connect the dots to match the number needed. All right. And we're not going to be bothered with that. Sometimes you might have to add to form a double bond. You have to move your electrons around so that double bonds are somewhere. That means 4 or more electrons can make up multiple bonds. We'll get into that later. So let's wrap it up. To wrap it up, we define ionic compounds as metals and nonmetals or polyatomic ions when they form cations or anions. They make ionic compounds, which are crystal lattice structure, and the properties of that are having high boiling and melting points, brittle, good conductors of electricity, and molten or solution, but not as a solid. And we also looked at the representation of atoms, ions, and ionic compounds, along with some polyatomic. So that is the end of this lecture. Have a good one.